I got some deeply technical stuff here, so hopefully it primes you for the lunch ahead. Real quick, I did a poll in advance. I was really late on it. Can I get a show of hands of folks that are familiar with search? Geospatial search, just to get a good feel for this. How about just LLMs, vector embeddings, or vectors in general? Okay, cool, good, all right. So I'll try to keep a good mix of some deeply technical stuff and also try to keep it somewhat high level as well, just to kind of, at least hopefully somebody, you get a little bit out of this. And if you are not really familiar with vector data structures or geospatial or dimensional data structures, hopefully when you walk out of here, you'll at least sort of know what IVFPQ is. Maybe. Real quick, background, our company Lucene is here. We have a table. We are really born out of Elasticsearch. OpenSearch is really what came from. My background, I spent 6 years at Elasticsearch building the geospatial data structures there and leading all their maps work. And I left right about the pandemic to go join the big cloud company that everybody's familiar with. And really quickly got sucked into their ODFE stuff and quickly pushed them to fork Elasticsearch. So I created the OpenSearch project, a fork of Elasticsearch as an attempt to try to stay as open source as possible. And then I just recently, earlier this year, we spun off and went sort of our separate ways and created Lucene to really start to break down search into just the small components that really make it fast and not carry all this big behemoth code that AWS has in there for a whole lot of nonsensical cloud integration. So that's really what we are. We're focused really on this problem, the fact that there's so much waste out there, 72 billion wasted on cloud infrastructure, storage alone. In 2024, this year, 83% of companies are looking to just get out of the cloud and use it for what it's good for, which is mainly another person's computer that scales. One of the big numbers that we had talked to some folks about was that for the amount of money it costs to store 5 petabytes of data, you actually pay for that over and over again. It's about $100,000 for 5 petabytes of data per month. And so you can store that on your own cloud server with triple redundancy for the same amount of price, or the same cost locally. And so we're looking at sort of that problem. How do we bring cloud spend down? How do we look more efficiently at the search data structures and keep this unnecessary storage at bay? So my talk today, that's where we're coming from. We're really built on top of the Lucene open source project. So about 10 years with that project, one of the long running PMC and committers. All the geospatial indexing was folded back into the Lucene project. And today I'm going to talk a little bit about some of the new advancements with at least HNSW, and then how we're starting to augment geo with some of the vector search data structures. So I'm going to break this down into kind of a 3-part. The first is going to talk a little bit about the evolution of spatial data structures inside of Lucene. And then I'm going to go into improvements that we made for coverages, shapes, how we handle the large number of points that represent a polygon, how we handle that problem, and doing spatial relations very quickly. And then what the foundation of that data structure is really rooted in is what vector indexing structures are all about. So I'm going to tie and show you how geospatial sort of set a foundation for that vector data structure that's out there, and then how we can actually leverage both against each other to do some of your retrieval augmented generation or hybrid search type use cases. So that's our journey here. Let me give a little bit of background on Lucene. Raise a hand, how many folks are familiar with Lucene? Okay, cool. So Lucene started, it's one of the longest running Apache software projects. I think we celebrated our 23rd, 24th year in existence. And it was really started around the whole idea of unstructured text. That's all it was, is it handled unstructured text very well, and it did it with one data structure called an inverted index. That grew to be able to support other use cases. And so, obviously the inverted index as a sledgehammer doesn't work for all of your use cases cases, even though they tried, even though for numerics, they would use an inverted indexing structure. So Lucene over the years has evolved to support sort of a collection of data structures, and it's really just a search API. In and of itself, it doesn't scale, it doesn't do any of your distributed system orchestration. That's really what Solr was about, and then Elasticsearch was nothing more than, hey, the APIs of Solr are not very good, so let's create something that has a better API called JSON. And so it's really, the project has just sort of evolved from that to have all these different kinds of data structures. This is really the core 6 right here, inverted index for text. We added, as of Lucene 6, KD trees. Specifically, it was geospatial driven. This is about the time I joined Elastic, trying to bring a true numeric data structure to Lucene. It didn't exist, so we had to create we had to create a tree structure, so it was rooted in what's called a block KD tree structure for numerics. Then we evolved that and tried to apply that to vectors, but I'll talk a little bit about why that didn't quite scale. So we pivoted around the time that HNSW started to become really popular and started bringing the HNSW graph data structure as its own independent, as part of the collection. And then you have these other 3 off to the side, which are accelerated for numeric analytics. So doc values is your columnar store. Then there's a norms format for doing relevancy and scoring. And then you have your document store, which is nothing more than the original data that you give it, because all the other data structures at some form or factor, they transform or mutate the data to where it's not even legible anymore to a human. So you have to have some kind of retrieval system. So that's really the Lucene in a nutshell. It's a collection of all these different data structures, and then they all work together. So that sort of sets the stage for the retrieval augmented, or hybrid search or retrieval augmented generation story here, is that we have all these data structures that can start working in tandem and leverage the strengths of each other off of each other. So that might be a lot of gobbledygook to some of you, so let me give you an example here. So this is where Lucene started, the inverted index. For those of you that aren't familiar, it's nothing more than the index in the back of your textbook. That's all it is. It's very simple. It's broken down into 2 sections. There's something called the dictionary, or the terms dictionary, and then there's something called the postings list. So this would be the equivalent of the terms and then the page number. That's all this is. So to give you an example of 2 documents, in this instance is 2 sentences of unstructured text, these 2 individual documents will actually go through an analysis or analyzer process, where stage 1 of that analyzer process is a tokenizer, and that just means that I'm going to get rid of all my spaces, and I'm going to take each word individually, and then it's going to go through a stemmer or a stop word filter, and those are just various implementations to say that, hey, I probably don't want to index the word the, because when I search for the, it appears in almost every sentence, and so it'd be a waste of space to do that. So that'd be called a stop word. Let's get rid of all the thes, the ises, all those really simple words that appear in every sentence that we speak. And then stemmers, which the prefix of a word, the postfix of a word, and then getting down into the root of the word. This is really the power of Lucene, where the developer community started developing all these different analyzers to analyze different languages and different text stemmers and filters to get it down into a very efficient and compact dictionary. Then the postings list is nothing more than a prefix encoded, compressed set of set of bits, right? It's a bit set where you just flip the bit to say based on the index of what document that you're looking at. So that in a nutshell is what the inverted index is and how it's implemented. This, believe it or not, was then repurposed, that's probably the wrong word, misapplied is probably the better word, to solve number search and numeric range search. So let me show you a little bit about how that was done and why it was bad. So here I've got a collection of 5 documents with a field in each one of them called my integer. And I picked integers just because 32 bits will fit nice and tidy on a screen. But this did expand up to 64 bits. So just double this size and you'll see how ridiculous this gets really quick. So take what I just said with the text data and apply it to the bits of a number and do the same process, but you're going to do a single bit step. So I'm going to break this down into a prefix of The most significant bit is 1 here. You can see that most significant bit is 1 for all 5 documents. So for 1, I'm gonna have a postings list of document 1, 2, 3, 4, 5, all 5 documents. Then you start to get into the variances. Bit number 2, you can see 1 and 0 both exist for documents 2, 3, and 4, but 1, 1 exists for documents 1 and 5. Then continue to bit 3, bit 4, so on and so forth. So very quickly, you can see for one number, I have 32 terms in the terms dictionary. For another number, I have 64 terms in the terms dictionary. And then very quickly, the terms dictionary starts to explode with just a collection of, small amount of numbers. So in terms of scale and big data, no, it doesn't work very well. But it is efficient for range searching, which is why it was used in Lucene to begin with, to do range queries, where I can very efficiently, decompose the data down into a lower resolution set, and then just do some post filtering to get the higher resolution and get the exact numbers that you want. So it worked, it just didn't work very well, and the amount of data that was stored on disk was astronomical. So scale out to 2020, 2024, that time range where everybody goes to S3, and for just a handful of numbers, you're gonna have a crazy amount of data that you're paying money for on the cloud. Not a very good data structure for numerics. Sorry, I had nice animations for this. Okay, but I think you get the picture. Let's expand that out to geospatial. So this then got probably misapplied for geospatial. But the big thing, 10 years ago were geohashes. Everything was a geohash, and all the problems associated with that on nearest neighbors are not so near started to rear their ugly heads. But look, let's walk through that same idea. It's a space filling curve. So I'm gonna take the first bit, it's gonna be the Y. I'm gonna take the second bit, it's gonna be the X. So bit number 1, I split the Y axis. Bit number 2, I split the X axis, and I just recursively do this, and now very quickly I have a bitwise hash to represent a cell on the Earth's surface. Probably everybody here is familiar with this. This is how tiles work, this is how tile encoding works, and then if you base 32 encode them, you get nice little string representations that people would throw on business cards for where they're from. But the problem here, of course, is that if I take that space filling curve and I stretch it out like a shoestring, points that are maybe within a mile of each other could end on completely opposite sides of the space filling curve. So really what we're doing is we're rasterizing a vector. And we all know that if we rasterize a vector, we end up with very large image cubes that end up taking a lot of space on disk. So why rasterize a vector when you can just do things in vector space? So at search time, we then have to rasterize the vector of a distance search, which would get turned into a circle. And now you have a quad tree representation of a circle, and a whole lot of millions of terms just to represent that one circle that I have to traverse that index. And then if I try to do very complex shapes, I very quickly see, those of you that are, remember the Netscape Navigator days when we would transfer an image, we would do this with quad trees using the same kind of concept, space filling cells. And so you'd have to have very low depth, or very high depth, I should say, millions and millions of cell to get the kinds of resolutions you want, because we are in raster space, right? Let me continue here. And then that document ID for that one number gets posted on the postings list, but now I very quickly have maybe several megabytes to represent that one image, right? So it works, but the consequence is pretty bad. And then we have to, in raster space, figure out all these different parameters to say, well, you know what, let's cut corners. I may only need 3-meter resolution. But then you get military applications come in and say, I'm sorry, I need higher resolution than that. This just doesn't work. And then my cloud scale ends up blowing out my S3, and then I'm paying millions of dollars in cloud costs. So, and I don't know how to tweak these for different types of use cases, and then I have to re-index. These are all the problems that we would face when you can tell I have some PTSD from on-call at Elastic. So we turn to the science, and that's what we do when we need something better. And we really looked, we didn't discover trees. Everybody knew that trees and multi-way trees is a better optimization because your access pattern is consistent, especially if it's common height and it's not a malbalanced tree. But what we were really looking for on Lucene is something that worked well with our block structure. structure. So there's a very, very good paper out there called the block KD tree structure that works really nice in serializing blocks on disk, which fit well with our segments in Lucene. The gist of it is this. We have a space and we're gonna just partition it down, and we're gonna partition it down into multi-way, right? So an n number of children at every level, and now that n becomes the base of your logarithmic function. So log to the base n of m, where m is the total number of points in your tree, is gonna give you your access pattern, really the height of your tree, the depth of your tree. But that will be the access complexity for every leaf in the tree. So we partition that out into 3 cells. That becomes the next level. And then we continue this partitioning process. And we go down, we have this multi-way height balanced tree, which is what B trees look like in MongoDB and all these other text-based like relational databases and relational indexers. So what we're doing here for us, for this block KD tree structure, is we're actually gonna lean into other research, R trees, because we wanna support shapes, right? And so we need to somehow get a very complex shape down into a nice, tidy, manageable package that could be our key in the tree, and that's where R trees come in, rectangles, right? And so we use the bounding box of the rectangle to drive those internal nodes, and then at the leaf node, we actually stick our data. So we have a nice partitioning, and then we can use multi-threading to traverse the different sides of the tree, because we can traverse them independently based on the intersection of those rectangles. And here's an example of some real data that I had pulled from London. We just took this from the Planet OSM data. We use that as our nightly benchmarking on Lucene. We've used that for 6 or 7 years now, several million points just as a quick test. And you can see that the nice thing about this is that all the data is partitioned where the data actually lives, which makes it very efficient, no waste of space. So now we need to improve it for shapes. Well, what do? Do we go back to quad trees and we rasterize everything? No, so we're gonna lean back into the research and the science. And for decades, if you're a gamer, you follow the total number of polygons that can be rendered per second, or graphics cards were very quickly measured by the total number of triangles that they could measure per second. So let's lean into the graphics industry for how they very quickly do things like collision detection, and you'll find that the triangle is the most magical geometry, right? And the reason that the triangle is the most magical geometry is because, if going back to your math days, the right-hand rule, right? Doing the cross product in x cross y gives us a normal vector in the z direction. And so what you have here is, if it's, you do x cross y positive, right? If it's x cross y negative, we now have a measure of what side of a line a point falls on. And so this is the magic I'm going to show you in a second. Before I get there, let's talk about trimming space again. Go back to the quad tree and take this really simple synthetic shape that I had created, and I did this at 3-meter resolution. So let's quad tree represent this, aka rasterize this vector, and let's look at how many terms would be in the terms dictionary if we continued to use that inverted index. Okay, 8 vertex polygon, 1 degree by 1 degree decimal degree coverage area, 3-meter quad cell resolution, 1.1 million terms. That's how many cells for the quad tree to represent the shape for an 8 vertex polygon. Okay, so we rasterize the vector. What if we just stay in vector? Okay, that same 8 vertex polygon in vector space using a tessellator, which can break it down into triangles, ends up with 8 terms, aka 8 triangles, you can count them there, and 1.1 centimeter resolution. I skipped over something very important here. We are not storing the latitude longitude as 64 bits, we're actually quantizing them, meaning we're taking the 64 bits, we're taking the property of the Earth's surface, which is -180 to 180, aka 360 degrees, and then we are histogramming that. So we're taking those numbers, we're dividing them by 360 degrees, and we're able to squish all these points down into 32-bit integers. So we are quantizing a decimal point of 64 bits down into 32-bit integers. It is a lossy process. So those of you here on the vector front, when you hear things like product quantization or bitwise quantization, this is a lossy process where you are compressing your real data, your original original pure resolution data down into a smaller compact representation. But in geospatial, does it really matter? You're at 1.1 centimeters. If you need higher resolution, this is where we make our trade-off, and we just store the data as 64 bits, bigger index. But if I need gnat's eyelash resolution, it's a price I'm willing to pay. But look at the compression ratio when we do that, 138,236 terms to 1. Now, we just needed a representation of those triangles at the leaf node, which is what this little magic guy does. We have these index dimensions, which are the first 4 dimensions. That's just the bounding box of the triangle. And then it turns out we can do a nice little bit twiddling, where we take 2 bits to represent where one, here, so there's the triangle, or the bounding box. Now we take this, 2 bits, and we can represent where a triangle's point is either shared on which, edge or which corner or not. And then I can use that to do a little bit of trickery to store just the y and x of one number. And I can tell you, I can reconstruct from 3 dimensions, all 6 dimensions of the point, right? 3 points times 2. So what I'll do is I'll take, 1 here. I'll say if it's a 1 on the x, a bit of 1, that means I'm actually going to take the min x value, which is -10, and then I flip the bit to 0, and the y value is going to be 5.1. So this corner ends up with, x, grab the min x number, which is -10, and then 5.1 gives me that. And then I do the same here. I flip that. The 1 I can say is the minimum y value, flip the bit, and I have 3.1. Is that how I did that? The x is 3.1, so I have that one. And then I'm sharing the upper right corner. That's what 1, 1 tells me. So grab 1, 1, the upper right-hand corner, flip the bit, here's your x and y, flip the bit, here's your x and y. And that's how I decompose it back down into the original 3. And then now I have a 7-dimension point at the leaf node. Coming back to the right-hand rule now, in order to do my queries, remember I said x cross y in the positive direction is going to give me left-handed orientation. X cross y in the negative direction is giving me right-hand coordination. I have a way to tell you where the point falls along a line. Expand this out to a triangle, and if I go in counterclockwise around that triangle, if they're all the same sign, I can tell you if a point falls in a triangle or not. If any one of those right-hand rule calculations are opposite the previous one, the point is outside the triangle. So I now have collision detection. I can tell you if a point is in a triangle or not, and I expand that out to tessellating the boundary of Texas, and I can very quickly use my R tree bounding boxes to trim down to the smaller set of triangles I need, and then any point that intersects those triangles will be considered an intersection. And then I do this using edges. So if I have points that represent a polygon, I can do this for every edge of a polygon, but then I can get more interesting where I take a polygon query at query time, switch that into a tree, and then I can do tree intersections and very quickly give you intersections of polygons. Okay, so those are index sizes over time, and this is performance over time from 2018. The last time I snapshot that was 2022. We've since then, this is just to show you that our Lucene nightlies continue to go up. Okay, extending to vectors. Now I talked about these different data structures here, and these different data structures are representing for the different use cases. We're going to come back to this one in a second. Let's look at a little bit 2 vector data structures that are commonly used, H and SW. So on the quad tree, you have a foundational knowledge of what H and SW then actually is. H and SW, hierarchical navigable small world networks, a mouth of marbles, is nothing more than reduced resolution sets of graphs. So at the top level, you have a very reduced resolution, just like the quad tree had a reduced resolution set. Then as you traverse down to the next level of the HNSW graph, you have a higher fidelity graph, and then you traverse down, you have a higher fidelity graph. This allows you to do recursive searches very fast at different resolutions, which is why it's ideal for high dimensional data, much like a multi-way tree. IVF, inverted file index, product quantization is really two parts. IVF is like your inverted index, where I'm going to take, say, an 8,000 dimension vector. I'm actually going to break that down into smaller subvectors, and then I'm going to compute their centroid and give an ID for that centroid, much like I would give a page number in a book. And that ID is going to come back to the data in the actual vector. And then I use quantization like you do with the geo to get back the original data in the vector itself. So again, it's lossy though. So anytime you quantize or you see the word quantize, you are actually reducing the resolution of your data, and you just have to decide what price you're willing to pay. So let's look at some data here on the actual vectors themselves. So this was used by Elastic. This is a test data set that a lot of different vector indexers will use. It's a 500,000 vectors of 1024 dimensions. If you represent them in their full resolution form of float 32, you can see it's about 2 gigs worth of data. There's bitwise quantization, IVF product quantization will get it down into 7 bits. We just recently added 4 bits, and actually we just recently got 2 bits in there, which I think is absolutely ridiculous to an extent, but this seems to be the big trend, is quantize higher and higher because we're trying to reduce data. The problem with this is the lossiness is very hard to measure, and you end up with a whole lot of hallucinations because you lose the further and further down the quality of the data, you're ending up losing a lot of signal. And so what you really need is a way to retain signal and compress without losing the original representation or the behavior of what the vector is trying to represent, right? And so it turns out, lean into the science again, those of you that are familiar with this in remote sensing, principal component analysis is used quite heavily in hyperspectral image compression. It's a way for us to retain the quality of our signal while compressing the data itself. And so think like your JPEG days, right? Or if you do a JPEG, it will say, well, what resolution do you want to keep the original image of your kid picking their nose, right? Like, oh, I might compress that down to 10% because I don't know, it's like, I'm fine with it being blurry. I don't want to store that much on my iCloud instance. And so you choose your percentage of your quality. That's the same way in principal component analysis. It's going to tell you how much each dimension is going to contribute to the larger signal or represents the variance in the data. And so what you do is you take your dimensions and you start adding them up close to 1, and then you chop that off at a certain point. Now that's going to tell you these first X number of dimensions or principal components are going to represent the signal of the data with 90% quality. So what we did was we wrote a little analytic to do this. It will run principal component analysis over your data. You give it the quality number, and it will tell you the number of dimensions. What's the savings? Well, if we add product quantization on top of that, it gets really crazy, but you're losing a lot of signal there. If I don't do any quantization with 32 bits, I now took my 2 gigs and I'm down to about 115 megabytes using principal component analysis while retaining 32 bits of the data. Now, your mileage may vary. Whatever data set this 500K vectors is could have a lot of redundancy. So don't expect that level of compression for everything because it's really based on the redundancy in your data. And if you have a lot of unique characteristics being represented, you still, you may end up with 500 megs, but hey, 500 megs is still better than 2 gigs on a cloud instance. So we are going to now wrap this up with the RAG stuff. So the key thing I've glossed over here. So we have all these data structures, but what ties them together? Well, it turns out, much like the inverted index, the document ID ties them together. So inside of a Lucene segment, you're going to have files that represent these data structures, and then you have another file called doc ID, and what's inside each one of these data structures, what ties them all together is the doc ID in the inverted index corresponds with the doc ID in the vector index, in the KD tree, the columnar store, your norms, and your document store. That means if I have a document that has vectors, geospatial, text, numerics, IP addresses, whatever you want, right? A graph, I have a way to have all these different data structures correlating to one document that represents some phenomena in the world. This enables now your retrieval augmented step, right? So the retrieval is nothing more than search. So here's how I would represent this. I have a document that has a vector embedding that would come from a piece of an LLM, right? And then I can now slap a filter inside of my KNN query. This is your retrieval step. So now I'm going to use my search to drive and distill down to the vector embeddings that represent more accurately what I'm looking for. So in Geo, the typical, I'm using the cliche here, Paris, Texas versus Paris, France, right? And yes, that actually exists in Paris, Texas, if you haven't been. And this is the actual latitude, longitude. So what I'm gonna do is I'm gonna throw that filter inside of my KNN similarity query with a vector embedding that I'm looking for. So I take my text, my words that I'm speaking here, I convert that into a vector representation based on my LLM, right? I now have a vector representation of the data. I can then throw that similarity search at my index that has my vector embeddings in them, and I slap this additional filter on there, which would be a geodistance and a term that says Paris. I am now using unstructured text, geospatial, to filter down my vector embeddings, and then I'm using at this point, because that result set is smaller, I can now use exact nearest neighbor search. I don't have to use ANN, approximate nearest neighbor search, which is now going to reduce the hallucinations because I'm not approximating, I'm actually using exact queries. And so this is your retrieval augmented step. Your generation step is outside of this. You can turn that into creepy people trying to do, Olympic gymnastics, if you've seen those strange ones. So if you've seen the weird models in the generation step, but that's outside the actual index search and retrieval step. So that brings it all together, and I think we are right on time.